Hello, everyone. Thank you so much for joining today for our webinar titled GCMS Techniques for Troubleshooting Off-Flavor, Off-Odor, and Flavor Scalping in Foods and Beverages. I'm very excited to have Jamie and Lily here with me today. I am Amy Knock, and I will be moderating today's session. Before we begin, I just wanted to let you know a little bit more about how the webinar will run. The webinar is being recorded and the slides and recording will be available to you within 3 business days. A short Q&A session will follow the presentation today to answer any viewer submitted questions. During the webinar, you can also submit questions you have using the webinar sidebar menu. Select the Questions tab, type in your question, then hit the Enter key on your keyboard. Remember, you can submit questions anytime throughout the webinar. That concludes my very brief introduction today. Jamie and Lily, I will now pass it over to you and you may begin your presentation.
Well, thank you for that introduction. As mentioned, I'm Dr. Jamie Willems, and today, along with my coworker Lily Zathis, we're going to be presenting on techniques for troubleshooting off flavors and off odors in food, beverages, and related products with a focus on GCMS techniques. So in this presentation, I'm going to start with an introduction to off odors and off flavors, why they are important and where they can come from. Following this, I'll give a brief background on the analytical technique before I hand this over to Lily to talk about some case studies. So as I'm sure you're all aware, aroma and taste are important components of consumer appeal for a product, and together they make up the unique flavor of a product. And so the flavor of a product is important for its identity. That is, a consumer wants to know that what they're purchasing will have the flavor that they desire and that it will be consistent from lot to lot over time as they repurchase a product. As well, it's important to new product formulations to stand out from previous products as well as to stand out from your competitors. Flavor can also be an indicator of quality assurance. Off flavors can be indicators of issues with a product, which we will go into more detail in this presentation. And finally, consumer trust. As mentioned before, consumers want to know what they're purchasing and what they will be consuming. And so a flavor can be an important component to having a consumer come back again and again to your product. And so off flavors and off odors can be not only off-putting to consumers, but they may be a sign of serious problems. And off odors and off flavors can have many potential causes and many potential sources. And some of the major causes of off odors and off flavors include packaging issues, issues with ingredients, contamination, both chemical or microbial, as well as issues during transportation and storage. And so I'm just going to cover some of the major causes of off odors and off flavors. And the first we're going to look at is packaging issues. So this can arise from a number of different causes, including packaging incompatibility, where the package you select for your product is incompatible with that actual product itself. An example of this would be an acidic product degrading an uncoated metal can, and this can result in leaching of metal into the product, resulting in a metallic off flavor, and could be a potential safety concern if your packaging isn't food safe. Another issue with packaging incompatibility is flavor scalping. And this is when compounds from your product are absorbed into the packaging material. And this can result in a loss of flavor and odor molecules over time. This can result in a decrease in the product quality over time as these compounds are lost, and so you get an overall lower flavor intensity. This can also result in a change in your flavor profile, as certain compounds will be preferentially absorbed, resulting in a shift in the overall perception of your product. The reverse can also occur, as mentioned above, where you can get leaching, where unwanted compounds from the packaging material migrate into the product. This is common with certain plastics, as it can result in a plastic or chemical-like off flavor. And this is particularly of a concern in pharmaceutical products. As well, choosing an incorrect package can lead to product degradation, which in turn can lead to off odors and off flavors. So, for example, if you have a product that is light sensitive and you store it in a transparent container, this can lead to light-based degradation over time. As well, similarly, if you have a product that's sensitive to oxygen, storing in a container that is oxygen permeable can lead to degradation. For example, unsaturated fatty acids are very sensitive to oxygen and heat, and this can cause rancidity through the oxidation of these products. As well, choosing an improper packaging can lead to leakage and degradation of the package, which can lead to contamination. And so contamination is one of the most common causes of off odors and off flavors. It can be broadly categorized into two main groups. The first of these is chemical contamination. For example, this can arise from storage issues, such as leaching from a storage receptacle, such as a holding tank, leaching from packaging, which we already discussed, or just improper storage allowing contamination from the outside. Improper cleaning can lead to chemical contamination as well. For example, insufficient rinsing procedure can lead to cross-contamination if you're changing products produced on a line, or it can lead to contamination with a cleaning agent if it's not properly rinsed from equipment prior to starting a new batch. User error is another common cause of chemical contamination. For example, excess lubricant added to machinery during maintenance can contaminate your product line. And there's a lot of different ways user error can come into play here. For example, someone not paying attention and accidentally dropping something into a vat. Related, we can also get microbial contamination. Once again, this can come from improper storage. For example, a product that should be kept refrigerated or frozen being stored too long at room temperature, allowing microbial growth and the formation of off flavors, such as those related to fermentation. This can also lead to chemical spoilage, such as fat oxidation, which can also lead to rancid off notes. Improper handling can lead to microbial contamination, or hygiene, poor cleaning can result in unwanted microbes getting into your product. Related to improper storage, you can also have cross-contamination. For example, you might have a finished product that requires that has been cooked or heated during your production that is accidentally exposed to the raw incoming material. Finally, another common cause of microbial contamination is processing failure. For example, incomplete pasteurization can lead to viable organisms still being in your product at the end of production. The last major group of off-odor, potential sources of off-odors that I want to talk about is production issues. One example of this would be a failure of your equipment. For example, your oven failing to reach the proper temperature. This could lead to spoilage, but it could also lead to changes in your flavor. For example, think of baked goods. You want that nice baked aroma and that nice brown crust, say, for example, on a bread. And so if your oven isn't reaching proper temperature, you won't be forming those nice flavor compounds. A process failure can also lead to changes in the flavor profile. For example, a failure to complete a defatting step can result in rancidity down the line if that fat goes bad, but can also lead to a change in the overall flavor profile if your product ends up having a more fatty flavor than you would like. User error is another potential cause of off odors. For example, failure to recognize out of calibration equipment leads to improperly measured or processed ingredients. This can lead to too much or too little of an ingredient being added, or, for example, poor mixing resulting in pockets of flavor while other areas are without. And finally, ingredient issues. An impure or contaminated ingredient incoming into your process can lead to an off flavor in your final product, as well as changes in quality of ingredients with a new supplier. This might not always be bad. It might not be that the new ingredients are bad or have an off flavor themselves, but their flavor profile might be different, leading to a change in the final product that may not be desired. And in many cases, an off odor or off flavor is caused by a combination of these different potential issues. For example, a packaging incompatibility could lead to a failure of the packaging material, allowing for chemical contamination down the line during storage or transportation. And so how do we go about looking for the potential cause of an off odor in a product? And we do this through volatile profiling. That is, looking at the different chemical compounds that are present in a product that contribute to the overall aroma. And so the profile or fingerprint of volatile compounds contributes to the overall aroma of a product. And there are thousands of different compounds that have been identified as being flavor or aroma active. So as an example on the slide, I have the profile of a coffee product. And each of the peaks in this profile, or each of the spikes in the chromatogram, is representative of a different chemical compound that is contributing to the volatile profile of this sample. You can see there are quite a few. And below, I have a table that lists some of the ones we've identified. And as you can see, these have been associated with nutty, roasted, green, or fruity aromas, and that together, as a whole, they make up the aroma of a coffee. And so to look for off odors and off flavors, we work to identify differences between a good or a control sample and a bad sample. And so, as mentioned, there are a lot of different compounds that can contribute to the aroma of a product. And when we're dealing with things like foods and ingredients, you're not just going to see one or two compounds. You're going to see a wide variety. And it is this variety and their different ratios that impact the final flavor of a product. And so it can be difficult just by looking at a single sample to ID the compound that might be causing the off flavor. As for example, some compounds may be a desired part of certain products, but be responsible for an off flavor in another. Think of a stinky cheese, like blue cheese. These cheeses are often defined by having a strong aroma that can be traced back to compounds such as short-chain free fatty acids. And while that would be a normal and desired part of the cheese, if you add those compounds to, say, a juice, suddenly you have an off flavor that might smell like a stinky feet. And so by comparing a good sample, that is a sample of the same product that does not have the off odor, to the off odor sample, we can look for differences. So, for example, compounds present in the off odor flavor or the off odor sample and not of the control could be indicative of contamination, say with a cleaning product, or perhaps spoilage, seeing elevated levels of free fatty acids or compounds associated with microbial fermentation. As well, we can look for the reverse, where there are compounds present in the control sample and not the suspect sample. For example, the control sample may have high levels of compounds associated with vanilla, which might be missing from the suspect sample, indicating that an ingredient was mixed during production. And so by identifying these differences, we can then look at these compounds and investigate further to look for a source of the off odor. So it's all well and good to talk about volatile profiles and off odors, but how do we go about actually testing for these profiles? And we do this using gas chromatography coupled with mass spectrometry, or GCMS for short. And GCMS is a powerful technique and our flagship approach for the analysis of volatile profiles. In this approach, compounds are volatilized and separated in the gas phase based on their affinity to a stationary phase, also sometimes referred to as the column. Once they are separated, they are identified and detected using mass spectrometry. And using mass spectrometry, we are able to look at the fragmentation pattern of these compounds. That is the unique way they break apart and compare them to our library of over 300,000 compounds, allowing for some identification of what is actually present in the sample. And so to give you a more visual view of how this works, so first, samples are introduced into the GC. So we do the sample introduction, and then they are separated on the GC column based on their boiling point and interaction with the stationary phase. Once these are separated, they enter the MS, where they are ionized with an electron impact source. That is, they're given a charge and broken apart. And then the fragments of these compounds are sent through the MS to be separated based on mass and detected by the mass detector. And that's how we get our output of our profile. So just to give you an example of what we can see, this is a total ion chromatogram from an essential oil product. And so on the y-axis, you have your intensity. That is the number of ions hitting the detector at any given time. And on the x-axis, you have your time. That is the length of time during the analysis of the molecules moving through the system. And so each of the peaks in this chromatogram represents a different compound that was present in the volatile portion of this sample. And we can get even more info here. As you can see, this is fairly complex. There's a lot of different peaks. But if we look at one peak in particular, say this one here, we can then look at its mass spectrum. That is the pattern of peaks or the pattern of masses we observe when we break that compound apart. We can then take this pattern and compare it to our library and identify this compound. And this is a compound associated with an evergreen and grassy tree-like aromas. And so in this way, we are able to separate and identify compounds that contribute to the overall aroma of a product. But the first step in this process is actually doing the sampling, that is getting it into the GC. And there are a number of approaches we can employ for this, depending upon the sample and the matrix in question. Our most powerful technique that we use is known as solid phase microextraction, or SPME for short. And SPME is a technique for the selective extraction of volatile compounds from a sample. SPME employs the use of fibers coated with a thin layer of polymer material. This material acts as an extracting phase, allowing for the selective extraction and concentration of volatile compounds. This can improve our sensitivity as we are concentrating these compounds before they are introduced. As well, it allows us to work with complex sample matrices as we can selectively choose our fibers to look for compounds of interest and help us avoid matrix interference. And we can select fiber coatings based on the compound class of interest. In addition, we can further tailor this approach by changing the chemistry of the sample itself. For example, adding high concentrations of a salt solution to promote volatility, or changing the pH to target acidic or basic compounds. So in solid phase microextraction, samples are incubated in a headspace vial to release the volatile compounds, which are then in the gas phase. The SPME fiber is then exposed to the generated headspace gas and allowed to equilibrate, giving time for compounds to absorb onto the fiber. Any absorbed compounds are then thermally desorbed into the GC inlet and analyzed by GCMS as explained previously. In addition to SPME, other approaches can be taken for sampling analysis, including headspace sampling. So in some cases, for products with really strong aromas, the concentration effect from SPME may not be desired. That is, that concentration effect can lead to an overwhelming of the system and can make it really difficult to differentiate differences between your control and suspect sample. So in these cases, we can employ headspace sampling. It works similarly to SPME in that you weigh your sample into a headspace vial and then equilibrate that sample at a given temperature to force compounds into the headspace gas. And then, instead of exposing it to a fiber, you take an aliquot of that unconcentrated headspace gas and inject it directly into the GC. This is useful, like I said, for highly aromatic products, but can also be used to analyze sample off-gassing when you're less interested in the whole volatile profile, but rather what's just naturally released into the headspace gas. And finally, another approach that can be taken is liquid sampling. This is generally the most common type of sampling for routine GC analysis when you're looking at pure compounds or a known compound that you want to get an idea of concentration. It is less useful in our case when we're looking at very complex matrices and an untargeted approach. In this case, liquid samples or sample extracts are directly injected into the GC. And this can be useful for semi-volatile compounds that are difficult to get into headspace gas. However, you have to consider that with liquid samples, you typically have to dilute them before you can inject them. And for solid samples, you would need to do an extraction first, which can result in selectivity of what you see depending upon the extracting solvent or technique you use. And so that's just a very brief overview of GCMS and off odors and off flavors. And now I'm going to hand this presentation over to Lily to talk about some case studies.
Thank you, Jamie. So now that we've gone over some of the background on what these techniques are and how they work, we're going to dive into some case studies. So we're going to look at GCMS data for real-world off-odor samples, and we will show you how we interpret what we see and then link it back to an actual product issue. So our first case study is an off-odor in a final product cookie sample. So during quality control sensory testing of a cookie product, the sample was noted to have a fatty, rancid aroma. And these cookies were produced using the same formulation as what had been used previously, but other batches had not had this off-odor issue. And so based on this, the client was hoping to identify if there was a specific ingredient change that may be causing this particular off-odor. So this is our first set of sample GCMS chromatograms. So what we have here on the bottom in black is our control sample, which had the normal aroma. And then on top in red, this is our suspect sample. And as Jamie talked about, each peak in this chromatogram then corresponds to a compound that has been identified using the mass spec fragmentation. So when we analyze samples like this, we're generating a huge amount of data, and we have a list of those compound identifications to go along with this chromatogram. So the first thing we look at is this has very clear differences, which is very helpful in this profile set. So we look for peaks that are not present in one sample or the other. And we also look at the relative intensities of existing peaks between samples. So that means we compare the heights and areas of the peaks that are already present. In this case, we have three very obvious peaks that are present in our suspect sample, and they are not present in our control. And these are caprylic acid, capric acid, and lauric acid. So these compounds are free fatty acids, and elevated levels of free fatty acids are associated with fat breakdown. And they also have sweaty, cheesy odors associated with rancidity. So microbial growth can cause the production of these free fatty acids, but in this case, we did also do a microbial analysis of the cookie samples, and there was no indication that there was excessive microbial growth compared to the control, so we could rule that out as a cause. So in this case, we were looking at the production of these free fatty acids and rancidity due to lipid oxidation. Additionally, these three fatty acids are the major components in coconut oil. So in this case, we were able to directly link the rancidity to their particular coconut oil ingredient in the product. Our next case study is looking at potential contamination in a fruity drink. So a customer discovered an oddly colored fruity drink with an unusual aroma, and it made them question if it could have been contaminated. So the drink, which was usually bright red and fruity, had a much darker color than expected and a chemical-like odor. So once again, we have our suspect chromatogram on the top in red, and on the bottom we have our control in black. So you can see these profiles are more complex than what we saw for our cookie samples, and this is also a zoomed-in view so that you can see some of the minor peaks here in addition to the much larger components. So I'm going to highlight we picked out several compounds here that we thought would be of interest, and these are isopropyl alcohol, 4,1-methylpropylphenol, and 2,4-dichlorophenol. So these compounds are all solvents. They are associated with cleaning products and disinfecting agents, and this strongly supports that the sample was contaminated because these compounds are not something that you would find in a beverage product, and they're not potential degradants. They're not something you want in your product. So we have now established we do believe contamination has occurred, but we don't have any information from our GC data that would explain why we have a difference in coloration. So based on this, we decided to look into this further, and we did another analysis using an internally developed and validated LC-UV method to screen for the major FD&C approved dyes. So these are the 7 compounds that are approved for use for coloration in foods, drugs, and cosmetics. So these are the common things you'll see on the back of many colored food products. So liquid chromatography analysis produces similar data when you're looking at it as what we've seen for the GC so far. So we still have our time scale on the x-axis, and in this case, we're looking at absorbance at specific wavelengths on the y-axis. So in order to analyze for these different colored dyes, we have to monitor at several different wavelengths. So this is our control sample profile, and we see a nice peak here for Allura red, which is red 40, which is what we expect for the product. And this is our suspect sample. So we still see our expected peak, red 40, but we also see another peak here for brilliant blue, which is blue 1. And so the conclusions in this case was that we confirmed that contamination had indeed occurred, and based on our LC-UV data and also our GCMS data, this suggested that they may have had contamination from a blue-colored isopropyl alcohol-based cleaner or disinfectant agent. Our next case study is looking at packaged goods. So this study is a little different because we are looking at an off-odor in packaged goods instead of a food product. And this request came from a distributor who noticed a strong chemical off-odor in several products, and that included goods that were both bottled and bags. So in this case, we weren't interested in comparing specific food samples. So instead of weighing our sample or pipetting our sample into the Headspace vial and then analyzing the Headspace gases, we actually sampled the gas directly from within the samples and used direct injection of that gas. Oh, pardon me, we used SPME to concentrate those samples then. So these are our sample chromatograms. Once again, in this case, these are a little different because up to this point, what we've looked at is total ion chromatograms, or TICs, which show the total ion intensity in our scan range throughout the analysis. So what we're looking at here is extracted data, which is taken at one specific mass of interest. So extracting masses in this way can be very useful when you want to look for low levels of an analyte, and these extracted channels can also be used for quantitation if needed. So in this case, in our TIC, we noticed a peak around 12 minutes, and this was identified using our mass spectrum, which is shown here as styrene. So we wanted to look for very low levels of this compound in our suspect samples, and so we produced these extracted chromatograms at a mass of 104, and then that is what you're seeing here. So our control, you can see by extracting, we've cleaned up our background. We have very few other peaks, and we have our nice distinct peak identifying styrene in our suspect sample. So we did find styrene in all of our suspect packaging, which had the chemical off-odor. And this compound is known for that odor, and it's also very common in industrial uses for the production of plastics, resins, and many other things. So in this case, they found that they had a contamination or leaching issue where multiple types of packaging had been contaminated with this chemical agent. Our next case study is a dairy product that had an off-gassing issue. So manufacturers of a newly developed fermented dairy product noticed that some of their samples were starting to have foaming at the surface and a sour, unpleasant off-odor. So you'll notice right away we have the same major peaks between these two samples in our suspect and control, but the intensities are very different. So these peaks here were identified as ethanol, acetoin, acetic acid, and 2,3-butanediol, and they are all elevated in our suspect sample. So these compounds, in particular ethanol and CO2, which is produced during fermentation, are associated with the fermentation process. And so this is aligned with the foam production we are seeing in the samples. And we know that the pathways for fermentation produce these different precursor and products as well. So in this case, we have seen this pattern in other case studies before, and this is an indicator that they had an over-fermentation occurring in their foaming samples. And that was why they were having both that foam buildup and the difference in aroma. Our next case study is a consumer complaint about a floral aroma in their package of table sugar after they opened it. So sugar, as you would expect, has very little volatile profile. So that is what we're seeing in our control sample on the bottom. However, our suspect sample has a wide range of peaks, as you can see here, that we wanted to investigate. So to highlight several here, with orange, these are all solvents, so that's acetic acid, propylene glycol, and many others. And then some of these minor peaks here, these are all fragrance agents with strong floral aromas. So that answered our question pretty quickly on what was causing that powerful scent. So with this abundance of these different types of compounds in this mixture, many of these are common ingredients in a variety of different scented products. So this could include things like cosmetics, soaps, detergents, and cleaners. And so they had a clear case of contamination. And in this study, we actually got more information after the fact. So the manufacturer was fortunate that they could provide a control sample that was from the same lot as the suspect sample. And so we were able to confirm that the contamination had happened on the consumer end and not within the manufacturing facility. So in addition to off-odor analysis, GCMS can be useful in general profiling when you want to compare samples for a variety of reasons beyond looking for a specific issue. So if you want to analyze for volatiles, you can look for impacts of a processing change, or what an ingredient is contributing to a product, or what storage conditions might do to a product. And all of this information is also useful during product development. So analyzing for full GC profiling can give us a lot of information as well as help us solve product issues. So as an example here, this is the full volatile profiles of a flavoring agent. And on the bottom in black, we have our original sample. And on the top, we had a client was working on re-engineering this formula. So I'm going to highlight a few here. So when we have this information, you can see these are very complex and intense profiles. And so we focused on different types of flavor compounds and aromas. So all of these red arrows are indicating herbal and woody components. And all of these blue arrows are indicating floral. And then in green on the right, we also have some vanilla compounds. So altogether, these are what is forming that specific character of each of the samples. And you can see, looking at it, that generally speaking, we do roughly have the same profile in some regions of the chromatograms, for example, the beginning part. But generally speaking, the intensities were much higher in the re-engineered sample. So both samples had very complex profiles using this analysis, and we found that the re-engineered flavoring then had a greater variety and higher amounts of several different compounds that would contribute herbal, floral, and woody notes, which included things such as linalool, geraniol, as well as pinene and other terpenes and eucalyptol. So with this information, the client was able to figure out what steps they wanted to take next in their re-engineering process, because they could really see how their changes had impacted their product. There are several additional techniques that can be used alongside GCMS full profiling that can be very useful in these investigations. So one of these I'm going to talk about quickly is a follow-up technique that we can offer, and this is GC-MSMS, or GC tandem mass spectrometry. And this technique is similar to what we've described, but instead of looking for a full scan mass range, we look at one specific precursor ion mass, and we look at one specific ion that it breaks into. So this means that even if you have several compounds with the same mass, they are very unlikely to have the same fragments. So by doing this type of scanning analysis, we get extremely good sensitivity and selectivity, and we can use this for trace analysis or low-level quantitation. So this is a good technique to offer as a follow-up in many cases to an off-odor investigation after we have identified compounds that are of interest. There are several other complementary approaches for this type of analysis because GCMS does not always show volatile differences when there is an off-odor or an off-flavor. And so some of these techniques include metals analysis for metals or heavy metals by ICP-OES and ICP-MS, as metals can have a strong impact on a sample flavor. Microbial analysis, as we talked about, is also very important as this is a fairly common cause of different off-odors. Additionally, sensory panels can be very helpful in giving very specific information about what the different notes are that are causing problems in the sample. And acidity, alkalinity, and peroxide values can also be measured, as these are very important in organoleptic properties as well. And then finally, we can also do full non-volatile screening using LCMS. And this technique is very similar to what we've talked about here in concept, but we are looking specifically at the non-volatile components in that case. So GCMS is a powerful technique for off-odor analysis and volatile profiling, as we've talked about here today. And by comparing the profile of a control and a suspect sample, we can identify compounds that could be responsible or related to an off-odor. And then with research and work on the identification, we can hopefully identify and correct the underlying issue. So thank you for joining us today, and I'll hand it back to Amy so we can look at some questions.
Thank you so much for the presentation. We did have a few questions that came into the chat, but certainly continue to ask those and type those in there. So the first question that did come in today, what kinds of techniques can be used if an off odor or off taste cannot be detected by GCMS?
Sure, so I can take that one. So as Lily just talked about, there's a number of different approaches that we can employ. So it kind of depends upon exactly what we're looking at. So if we don't see it by GCMS, that probably means it's not volatile. And so if you're looking at, for example, like a metallic type off flavor, then I would look at metals analysis, as that can lead to that type of off flavor. If you're looking at something more plastic-like or chemical-like, then I would look more at like LCMS to look for non-volatile compounds that are known to leach from plastics.
Great, thank you. The next question that came in, approximately how much sample do you need for this analysis, and what is the minimum amount of sample required?
So when we're looking at sample amounts for this kind of analysis, as Jamie said, in many cases, these end up being specific to the issue. So if you have a very powerful scent in your sample, we often don't need a lot. So we're talking normally in the few grams range, depending, or a few mils. It really depends on our sample, but we do also have techniques if we don't have a lot of sample to work with. As Jamie talked about, we can work on promoting the volatility of what is there using saturated sodium chloride or pH adjustment. And we can also then modify our SPME fiber to really target in if we don't have a lot to work with.
Great, thank you so much for that. The next question here, are you able to perform analysis if you don't have a control sample?
So I can take that one. So theoretically, yes. So we can look at a suspect sample, look at the profile, and so get that profile and look for peaks or compounds that might be typically related to off odors. However, this is very challenging, as I mentioned, some compounds can produce an off odor in some products, but they might also be normal and part of the flavor profile. So ideally, we would want a control sample. In the best case scenario, we'd have a control sample that was of the same product, maybe just a different lot that didn't have the off odor. because it makes the comparison and the ability to kind of troubleshoot and look back to the root cause a lot easier.
Great, thank you for that. And looks like we have one more question here, and that is, once you've identified a potential source of an off odor, do you have any recommendations for confirming the cause of it?
Well, I can take that one as well.
Okay.
So once again, it kind of depends upon what you're looking at. So, for example, say we identify compounds typically associated with microbial fermentation. In that case, I would suggest a microbial test, looking for yeast and molds or aerobic plate count, see if it's elevated in the suspect sample. If you're looking at something like, say, a potential cleaner, we could do, as we showed in one of the case studies, potentially looking for dyes associated with cleaners. Or if it's a volatile compound and you want to confirm that that's the issue, another way to do it would be to look at multiple lots of samples, maybe that have that off flavor, or even that don't, to look to see if it's consistent across all of the lots.
Okay, perfect. And it looks like we are all caught up with the questions at this point. So I think we'll wrap up here with today's session. Again, I want to remind everyone that a recording of the webinar will be available to you within 3 business days. Thank you again so much, Jamie and Lily, for the presentation, for your expertise. And thanks again to everyone for attending. Have a great rest of your day.